Okay. Good morning, good afternoon, everyone. My name is Amir Ashuri. Thanks for the invitation, Mika. So I'm gonna present MLGOPerf and ML guided inliner to optimize performance here. This work has been done in our lab in Toronto, Canada, in Huawei Heterogeneous Compiler Lab. And at first, I'm gonna start quickly by looking into the pros and cons of function inlining in LVM and in
Amir,
general. Yeah,
Amir, sorry for interrupting. Elop was asking, are you okay recording this, or I'm not recording, but do you want me to record? Are you okay with us recording, or
sure. Actually, I'm also
we can?
recording it
Okay,
on my side. Yeah.
you
Feel
are
free.
recording.
Yeah.
Oh, perfect. Thanks. Okay, so if you can share it afterwards, but awesome.
Okay.
Thanks.
Sure. Absolutely. Yeah.
Okay, sorry about that.
No worries.
And thanks, Elop, for asking.
All right. Okay. All right. So as you all know better than me, function inlining has both pros and cons. On the pro side, it's going to reduce the overhead due to entering and exiting the functions. At the same time, it's going to eliminate the instructions required for function calling, and also in certain cases it's going to reduce register spilling. And one of the other important features about inlining is that it's going to open opportunities to subsequent passes in a pipeline, and some other optimizations can benefit from inlining. On the negative side, obviously it's going to increase the code size, and on aggressive inlining, sometimes larger code size can reduces the temporal locality, and it's going to hurt the memory hierarchy of your runtime. So there are several factors to consider when you inline, one of which is the call size, and the other one is how hot of a call site you are trying to inline. If you look at LVM, it has many magic numbers and threshold involved. Normally you can find those inside inline cost, as I brought here in a screenshot. There are several factors to consider when LVM tries to inline a function, and I'll quickly go over those. But as you see, there is a lot of variables and magic numbers involved when you do an inlining. As a small example, so assume this is your color and you have three call sites in your color, and these are the calls to the callee. So if you inline those three call sites and you're going to have the function body inside the color, you're going to end up something with this. And in LVM, normally inline optimization is done at the IR level. However, if you take a look at the O3 pipeline, and this is the whole bunch of optimization inside O3. It's almost maybe 160 optimizations. Maybe 60 to 70 of those are unique, and several of those are getting repeated in subsequences of small passes. So the one that I highlighted here, which is not totally visible, is the inline. So you see there are so many optimization after inline that can benefit from an intelligent inlining. Normally in LVM, at low optimization levels, it is disabled, or we can control it with explicit use of attributes such as always inline attribute, or certain command line arguments such as always inline or disable inlining. But at O3, it is enabled by default and has been used only once in the pipeline. There is also a usage of inlining at link time optimization, especially at LTO, but this is outside the scope of MLGOPerf for this work. I mean, obviously, when you do that, it's going to open up some intermodular optimizations or interprocedural optimizations in LVM. All right, so going back to LVM and the overall heuristic of inlining, at IR level, which is the target of this work, it's going to build the call graph for the whole module, either using the lazy call graph or the old call graph, depending on the new or legacy path manager that you're using. And it's going to iterate the graph bottom up, and for each call site, it's going to simulate the effect of inlining, and it uses some heuristics to estimate the cost of that inlining. As I mentioned in a few slides ago, There are several magic numbers involved with estimating the cost. And on the other side, it's going to go and find the estimated threshold that it is able to handle the inlining. So that threshold also can be passed as an argument, command line argument by the user. And basically, it's going to check if the cost was greater than threshold, so we're going to inline. Otherwise, we're not going to inline. So that's basically what inlining has been done in LLVM for now. And as you all know better, in April of 2020, Google released the MLGO, the first version of MLGO, and it was later upstreaming to LLVM. There are several more qualified people in this meeting. Yes, so yeah, it's an LLVM thing now. Yeah, sure.
It was never a Google thing. MLGO just says ML guided optimizations. It's not a Google technology.
Sure.
It's an LLVM.
Yes,
yeah,
yes.
So I'm just saying, like, yeah.
Right. So it's upstreaming to LLVM, that's the paper that you can find more information. The authors find that by intelligent inlining, they can outperform OZ of LLVM, which is the code size reduction standard in LLVM. Feel free to refer to this paper and ask questions from more qualified people here. All right, so what we've been doing with MLGOPerf is we wanted to extend LLVM MLGO to target performance rather than code size. So MLGOPerf, in this methodology, we applied a secondary ML model, which we called IR2Perf, and IR2Perf allows us to have a post-inlining speedup so that we're going to generate rewards as needed for the second model, in that case, which would be the primary model that it was already being used for the first version of MLGO, so that the rewards are getting generated for the RL model at each iteration, and we don't need to run the the code every time to train the RL model. So with that in mind, IR2Perf needed to be trained, and we leverage our auto-tuner to generate around 300K plus meaningful inlining configuration, for which we use a spec benchmark on that on ARM. Since as you know, spec has multiple datasets to use, so the ref dataset is the largest one. So we couldn't simply afford to run all of those iterations with a large dataset. We use the train dataset, which normally takes around 10 to 30 seconds to finish. And so we thought by leveraging the train dataset, we are able to train a model that eventually is going to help us to outperform spec on the ref dataset. So in order to characterize the applications that we were trying to generate training data for, we iteratively generated 20 handcraft features. I'll show you later in the slides. And as I mentioned, we leveraged the IR2Perf to train the RL model, and for many iterations. And then you can assume if we weren't having the IR2Perf here, simply it wouldn't be possible to run the spec or whatever training data you have for more than 1 million iterations in a timely manner, let's say. So this is tons of information here. So this is roughly speaking the class hierarchy of MLGO. So there are several components here, and I'm not going to talk into details because the details are already published, and also that they are in LLVM now. But basically, they have 3 enum classes of inlining advising mode, which is default, release, and development. With development, you can train your RL model. With release, you can deploy that when it was trained, and it's going to control the inline advisor, which is dealing with also in this case an ML inline advisor. So what MLGOPerf added here was to adding another analysis pass to generate features for both our RL side and also our IR2Perf side, and then all of the corpus or the training data we use to generate that. And then we sort of extend this model in order to, on the development side, we use MLGOPerf inference to generate rewards for the RL model. Yeah, I know the details are too much. I'm not gonna go into details, but feel free to have a look at the MLGO paper, or if you needed more help, just feel free to email me. So if we zoom into MLGOPerf, high level flow, we notice that these are the two models that we used. So the first of which we called IR2Perf, is a supervised learning model. So we wanted to characterize function features, and as the output of this model, we wanted to have the function speed up post inlining when inlining happens. So if we able to generate that could be used as reward at each iteration for the existing RL model, for which it would decide on each callee whether or not to inline. So the action would be whether or not to inline. It's a Boolean action, but at each state you need different set of features. So on the first model, the characterization is done by the features of the whole function, right? But the second one, the feature list is a little bit different. Is more pertains to the callee one, so that it generates more meaningful data, and then when we drive an action using the reward, it's going to get the action right. So you can easily notice that when we have two ML models, we're going to be having three phases. The first phase would be just a standalone training of the first model with the data we have. So in that case, RL model has nothing to do here. On a second phase, when the first model is trained, you want to deploy that. So you, at each iteration, you want to generate rewards for your second model under training. So that's why in the second phase, you have an inference of IR2Perf and training mode of RL model. If you go back here, that training mode is under development mode, right? And on the second phase, when this one was sufficiently, quote unquote, sufficiently trained, you're going to unplug the IR2Perf and you're going to deploy.
Hey, Amir, I have a question.
Sure, go ahead.
Yeah, the question is, see, at this time, are you still taking the reward on a per function inlining basis, or, say, for example, there are two function calls adjacent to each other? Would you have a reward where both of them are inlined and maybe you are getting new opportunities?
Right, that's a very good question. So I'll answer your question in a few slides, but in high level, we are accumulating both of those rewards together. I'll explain why, but thanks for the question. Okay, so and as I was mentioning, so at the third stage, so when we deploy the RL model, we simply unplug the first one, and it's gonna go on its own without needing for the reward, and it's gonna provide a standalone prediction for us. So this is basically all those three stages together. So if I want to, I hope this is readable. So the first phase, which is the IR2Perf training, we simply generate many configuration of inlining that has meaningful inlining impact on the code in different call site granularity. And then we have developed an analysis pass here written as collect features that collects features post inlining for us. And the subsequent passes of O3, as I mentioned in the earlier slides, is going to apply throughout the pipeline. So we get all this feedback and stats and save it in our quote unquote CSV file. And with data processing and pre-processing, we're going to be able to train IR2Perf. On the second phase, when we use IR2Perf as its inference, so we no longer train that, this will provide us the rewards, and this let's say this methodology is somewhat closer to the actual methodology of MLGO, for which at each of these call sites you're going to have to collect the features for RL, which are different than the features that we collected here for IR2Perf. And then what we plot here is the RL trainer for each of those iterations is going to ask us for a reward, and then the rewards will be accumulated for each module, and then it's going to sum up, and then you have one final reward per module here. On the third and the final stage, we simply build the sufficiently trained RL model and build it with LLVM compilation flow. And also there is a possibility to do ahead of time compilation, so you no longer have to load the model every time, and it's gonna generate your library to be used with the inlining. So let me just quickly go through those handcrafted features that I mentioned. We iteratively arrive at this point that there are other features that we use, and then we tentatively remove. Basically, for any ML projects, you need to understand the correlation between your features and your target metrics, and then several features might be take into account this factor in your ML development, and then eventually we're gonna arrive to these features that we thought it would generate meaningful results. So which x84, could you elaborate on that? Yes, for ahead of time compilation, yes, it's for x84, x86. Yeah, unfortunately we don't have that infrastructure on ARM, and we have been having many problems with that, because eventually we needed to do cross compilation at each iteration in order to make that happen on ARM. Hopefully this infrastructure will be out on ARM as well. All right, yeah. So this is the architecture of the IR2Perf. It's simply
Amir, one more question. Is your final prediction is in terms of total execution time or IR number or something?
Which prediction? The IR2Perf or the RL model?
Yeah, IR2Perf.
IR2Perf is a speed up with respect to the baseline, which is 03.
Okay.
Yeah.
Okay.
Yeah. So the architecture of IR2Perf is a simple 4-layer, supervised learning regression model, and this is the cross-validation results of IR2Perf. So you see, if we leave one out and then cross-validate using the rest, we're going to see that on certain cases we have lower, let's say, error rate, and on certain cases we have higher error rate, and the geometric mean was around 12%. So we were around 10 to 15% with the actual speed up values in this case. So these are a bunch of training flows. So you see that on the first epoch, the IR2Perf is getting converged pretty fast after a few batches, and this is how close we were in the training data. And this is one of the test examples for which we hold out that specific application and then we use it as test. So we are within 10 to 15% error rate on that end. So this is the line, the blue line is the actual speed up, and the red line is the predicted speed up for IR2Perf. Now going back to your, I'll answer your question in one slide. Let me just quickly recap the reinforcement learning. A much better description of this is in the original paper of MLGO. Yeah, I'll encourage all of you to have a look at that. But as a simplified version of that, for the RL model, so we are in RL basically is a transition probability that represents 4 entities here. So states or S, actions A, transition T, and also a reward. So basically what it does, it uses a Markovian process, and it's going to represent all of those states as some sort of action states, for which in our case was the current visiting call site, and an action that transitioned from a state S to S prime, and the transition T was a deterministic function in our context, for which when we update the call site upon each of those actions, what would change to switching to visit it to the next call. And the reward, as I mentioned, was generated by IR2Perf in this work, was defined as function execution time with respect to its baseline, which was 03. Now, going back to the very first question I was asked, yes, with IR2Perf, we actually could generate speed up independently for each of those call sites, but we decided to append those and aggregate them per module and then just return the total reward. Both ways would have been possible. I didn't spend time to explore on the first one. It would make the training of RL a little bit more tricky because you have higher number of updates in each module, so your RL would jump up and down much more. So you're gonna, I mean, it's gonna be a double-edged sword. So you might find better, convergence value, but at the same time you might be more lost because your update is way more, and actually the training will take much longer in this case. But for simplicity, we decided to aggregate those function speed up and then be updated once. So the procedure goes for the RL training. We initialize the policy randomly, and we're gonna iterate over our training data, and we're gonna sample the training data in our training set, and we compile it with that policy, and then we generate the function speed up of that specific module here using MLGOPerf, for which we're going to append all of those speed ups, and we generate a total speed up for that, and then using that reward, the RL will update policy-wide using the equation 1 returned in the paper. Hopefully I answered your question.
Yeah, thanks. Yeah.
Okay. All right. So let's jump into the results. We targeted.
1 second. Where is your equation 1 in the previous slides?
Sorry, it's in the paper. I can show you.
Okay.
Yeah.
Okay.
Okay. So the results, we were targeting both SPEC CPU 2006 and also Cbench on ARM. So there are several columns here. So we were targeting speed up with respect to the O3, and also we tried to control the measure variances here. We were using NUMA control to assign it to a single core. We used trim mean to run it multiple times and get rid of the highest and lowest value and take the average of the rest. We were flushing the cache at every iteration. So we tried our best to control the noise, because as you know, the margins are very low, around 1 to 2%, and we wanted to make sure this is not the margin of error we're talking about. This is an actual speed up. I actually did some statistical tests over that, such as t-test, and the distributions are actually having a meaningful changes. So the speed ups are real, but as you see, this is only 1% to 2% speed up you're talking about here. Speed ups with respect to O3 on a SPEC, we were on average 1.8% better. The variances was under control, almost 0.5%, and obviously MLGO, the original MLGO, wasn't trained for performance speed up, so we were definitely going to be better. On the other side, the code size increase as a price we pay for optimizing only performance was around 17% with respect to O3 and 23% with respect to MLGO. On the case of Cbench, we were around 12 and 16%, but the speed up values were a little bit higher, 2.2% on Cbench. The other, I guess, more important thing that we wanted to let's say focus on here is, as I mentioned in the earliest slides, inlining optimization can provide a wider scope of intermodular optimizations for the rest of the subsequent passes in optimization O3, and we sort of had a small experiment for which we tried to auto-tune two passes subsequent to inlining, loop unroll and loop vectorize, with 5 or 6 parameters, and we decided to use 3 versions, O3 versions, vanilla O3, MLGO version, and MLGOPerf version, and see when we apply that specific inlining at each of those method, what's going to happen to the subsequent passes, and at the end, what's going to happen to the final binary that's getting generated. So do we provide more opportunities for the subsequent passes? Do we hinder certain optimizations there? And what's going to happen to the code size as well? So that's why we explored for maybe 100 to 200 iterations of tuning. And after 200 iterations, we noticed that if you auto-tune C-bench by these two parameters, you're going to have around 2.5% speed up gained by playing around with these parameters of loop vectorize and loop unroll. Whereas with MLGO, you're going to have a little bit of higher speed up, 2.7, and MLGOPerf has a more meaningful speed up, provides us in the subsequent passes around 3.7. And if you take a look at the tunable regions, so each tunable region is actually one opportunity to tune. Let's say you have a loop unrolling opportunity for which you can play around maybe with the UP count of unrolling. So that would be one tunable region. So you see the tunable regions in certain cases hasn't improved much because perhaps maybe they were limited to only those regions. But in many cases, for instance, on the third case, we have like, I don't know, many more opportunities provided for the subsequent passes as a result of MLGOPerf inlining. So we thought this would be a more noticeable performance improvement by having a more intelligent inlining rather than the pure speed up values that you see here on the first slide. The other thing that I dug into, go ahead. Sure.
Sorry, one question to the previous slide.
Yeah.
So the speed up here is got with the auto tuning of your tunable regions.
Yes.
Okay.
Yeah.
Okay.
So at the end of the 200 or X amount of iteration, what would be the final speed up we could gain by applying different inlining methodologies? Yeah. Yeah.
Thank you.
No worries. Okay, so I dug into some of the results, and I really wanted to showcase one real case example. I mean, it was very hard to find a small enough application that has meaningful result that can be, readable in a short amount of time in a presentation. And I found this security SHA in Cbench. And so if you use the vanilla LLVM with a new pass manager, so you're going to see that certain call sites, and this is some coding snippet from SHA. So in certain call sites, the cost is higher than threshold, so we're not inlining at O3. So that's why I highlighted here not inlining these two call sites, right? And if you compile and then run it semi in isolation just once, I didn't run that like multiple times like the results in the paper, but I follow with the same flash caching and then NUMA control assigning to the same CPU, and it was in isolation. So we're gonna see that runtime around 8 seconds on x86, right? So I thought let's reuse this with MLGOPerf and see what's gonna happen. So if now you deploy MLGOPerf and use that in the release version, so you're gonna see those the final call sites also got in line. And as a result, when you run that, you're going to have around the 16% speed up on this specific case. I mean, it was small enough to pinpoint the call size, so that's why I brought it here. And I dug into the results that I generated previously as an exhaustive search. So if you exhaustively search for all the call sites that can be in line with security SHA, you notice that all of the decisions made by MLGOPerf are quite accurate, except one that we needed to avoid, inlining the final call site, which was the SHA_final. And by doing that, we would have had another 7% added to the mix. So the overall would be around 25%. So this is, I would say, a missed opportunity for the performance that MLGOPerf didn't get it accurately. I mean, as we are dealing with two ML models and the margin of gain is so low, sometimes there are several cases that we are far away from the optimal solution. And I just wanted to show that here that although we were providing a certain amount of speed up, we are still far from something optimal that all the time we're going to get the best results in the space.
So Amit, did you say that in the original one, this was not happening due to the inline threshold?
Yes, on this, if you run O3, O3 gets this right, but it's going to get several other cases wrong. That's why it loses 17%. we get those cases right, but this specific case wrong, and we have a certain amount of speed up over O3, but we are not as good as the optimal solution for which you exhaustively search all of the combination of permutations, right? Any other questions? All right. So I'm just going to wrap up my presentation with several challenges. I also mentioned them in detail in the paper. So as you all know, the IR2Perf, level of granularity was at function level, right? Eventually, we are trying to use 2 ML models to have a global speedup prediction, which is if you inline this call site, whether we're going to have a global speedup or not, right? It's always the case that these 2 metrics don't agree with each other. In certain cases, we found in our data that there is a function speedup, but the overall global speedup has gone down, or it was the other way around. And several factors are here, memory hierarchy, depending on the hardware, you're going to have this issue. So this is always an issue when you have 2 different levels of granularity and you want to predict one from the other. There is always a chance that you have some level of noise in there. The other challenge that we are dealing with, as I mentioned here in the results, original MLGO was only targeting code size. That's why it's much better than MLGOPerf. On the other hand, we are trying to optimize for performance, so we are better on that end. We are worse in the code size. So there is this multi-objective aspect, code size versus performance, especially an embedded domain, that we need to take into account. Several other papers have done Pareto optimality analysis and other stuff to take into account both objective, or there are several objective. But I just wanted to show that this is also an open question that we can target that. Yes, true, exactly. And I mean the general difficulty around the compiler optimization space, an MP hard problem. This is a known issue for the past 25 years. We were trying to predict performance or speed up. This is also noisy measurement. We did our best to isolate the problem and our servers. We controlled the page memory, and also we were running it multiple times, taking a trim mean. But still, there are always noise involved on that matter. The last of which is the software characterization. As you all know, there is a new trend of getting a graph-based representation. It would be awesome if you have, if we have, leveraged this. It is still a very hard problem to take into account. The graph representation or the dynamic way of generation of software characterization into the mix. Hopefully, in the future, we're going to see more and more of that into the space as well. With that, I'm just gonna leave you with the link to the paper, and also mention that we're gonna in about a month or so we're gonna present the short version in cases. Yeah, with that, I'll be happy to answer any other questions. Thank you.
Thanks, Amir. Awesome.
Thank you.
Amir, one more question. Oh, sorry, go ahead. Sorry.
No, just Johannes, go ahead. Oh, okay.
Please.
Thanks for the talk.
No worries. Yeah.
So let me play devil's advocate as I usually do because I like it so much. So you have this new model that is effectively an inline heuristic based on ML, but for all intents and purposes, it is a new inline heuristic, right?
Right.
And the results are we get faster code on average, but we get bigger code on average too. Why would you not just say, hey, let's just make the existing inline heuristic inline more? Like basically decrease the threshold or increase the, decrease the cost and increase the threshold which would result intuitively in the same inline choices, so that you inline more, get larger code, and hopefully more speed up. So what's the argument for doing that? Or have you tried and it doesn't work?
Yeah, very good question. Yes, intuitively, one might think that this would be an easier problem to tackle, but the difficult question is, in what way, right? How would you decide to inline more? Are you going to increase the threshold only? Are you going to, be more tolerable to certain, hot functions or hot call site? We actually had certain results generated maybe in 3 different versions. One version was to let's just play around with auto-tuning call site, inlining a call site just randomly, and say if complete random inlining can outperform MLGO, for which it wasn't able to. The other one was we thought, okay, let's just randomly pick up 75% of the call size and randomly inline those 75% and leave the 25% untagged. Also, MLGOPerf also outperformed that. So the third one was to now don't fix this 75%. At each iteration, let's pick 75% of the available call site and change that randomly. Also, MLGOPerf outperformed that as well. So we thought that, okay, it's not an easy problem just to inline more, because you can always inline more, but in what way, I guess that would make the difference. Even MLGOPerf, as I mentioned here, let me just go back. We are still far away from the optimal solution here, because we inline one more than it was needed, right? If we didn't inline this, we would have got the optimal results, which was another 7%. So there is definitely a room for improvement. I'm pretty sure there is higher speed up out there, and also the two ML model interactions, although seems very yes, as we have in the chat correctly, yeah, we're gonna have larger pressure on the instruction cache, and we're gonna have more cache misses. So in bigger applications like a spec with more copies, we're gonna have a slowdown actually.
That simple logic that Richard had posted there that might be true as like a rule of thumb, but effectively this heuristic inlines more.
Right. Yeah.
So with that simple logic, it inlines more. There would be more pressure tank performance, but that's not true. Right. So if you inline too much, you might tank your performance. But yeah, I would just say I take the cost and I reduce it by 10%, or I tune it. And as you said in the very beginning, there's 10 parameters there, maybe more, that you could tune. And now the question is, why do I have to do a model that I don't understand, rather than tuning those values? And your argument of, we did random testing of call set inlining, I mean, that throws away all the smarts of the existing inliner heuristic, which maybe you're not, but it's probably better than random. I would hope. I mean, otherwise I would be very disappointed. So why don't we say, what is the result if I really just inline, if I make the cost 10% lower, threshold 10% higher? Yeah. Will I get a little bit bigger code, but a speed up? Yeah. And if so, can I continue that trend to see where it leads me? And that is kind of the missing thing for me here, because this is just, let's not tweak the thing we have, but make a completely different thing, and we don't know if the tweaking would have helped.
Yeah, yeah. So let me just point out one more thing here, that if, for instance, here we have the cost as 420 and the threshold was 250, right? So we didn't inline. If we were to increase the threshold by 10%, even 20%, we wouldn't have made it to inline, right? Or on the other cases. And that threshold is having a very large value, I don't know, more than several thousand. I'm not sure if it's the largest U8 bit, or I don't know, some sort of 16,000 or 160,000 or something. I need to double check that. So it's not like in certain cases, especially on the larger call graphs, this threshold becomes very large. So it's relative to the application, and just simply having one constant addition to the threshold, I don't think it's going to help on certain cases that be more tolerable to inlining, right?
Constant addition, 10% off is not constant; it's relative.
Yeah,
or 10%.
I would say even 10% relative won't help here. So it's always the issue by how much and how we are intelligently enforcing that,
Maybe
right?
it won't help.
Yeah.
You don't like this is one example, right?
Yeah.
It doesn't matter if it helps here. We're looking at averages. So if it helps here or not is one thing. But if it's an average helping, that is the result you mainly produce. I mean, this case studies, whatever.
Yeah.
Sorry, Mitchell, you were saying something.
No, like I mean the tuning of thresholds is, I mean, basically captured that. Like the problem is it doesn't really, you know, it work. You can do it for one application and then you get some values. You get this for another one, you get some values. But that's not the point here. So you're right that you could do analytical, you know, like analytically you could arrive at improvements in heuristics, right? We've been doing that. We can do that. This is about, well, can you skip about a bunch of that manual stuff and get somewhere more automatic, right? So I don't know if that you see. I mean, like, I don't know if that helps or I'm just saying, like, I'm not looking at it as I could have gotten like 1% by doing something else. I'm looking at, can I evolve this further than 1% over time with more features and more data? And that's something that I cannot do with a heuristic, right? I'll just keep digging with the thresholds there.
That is a different argument. That is the argument.
Oh, okay. So I thought that I missed what you were trying to ask. Sorry.
That is the argument. Oh, now we can get rid of all the manual stuff altogether, with the hopes that the model-based thing is going to be easier evolved in the future and be, you can also more easily specialize that for your use cases and stuff like that. So the model has intrinsic benefits, but these evaluations where we just look at this are a little like, that is where my critique is, like, if you just look at the evaluation like that, you could have gotten more inlining decisions, probably inlining benefits by just inlining more. But if you say, hey, replacing the entire heuristic, the manually written one, manually curated one, with a model has other conceptual benefits, that's a different discussion, and that makes sense.
No.
We haven't actually figured out if all the benefits we hope it will have is going to come through in the end, but that's a different. Yeah.
One thing though, about the comparing. So I think it is fair to compare with the sheet, as baseline, because okay. So let me see if I understand you right. So you're saying, like, if you were to tweak the baseline, you could see, hey, could I, for a set of values of the thresholds, get, in quotes, more inlining, right? And compare it with that. Okay, I see. I mean,
the results now are basically the new model, the new inline heuristic inlines more and is faster. It generates faster programs because it inlines more, and we know it inlines more because it generates bigger programs. So that is intuitively makes sense. Now the question is, the main thing about inline heuristics is to pick the right choices to inline, right? And now the question is, could we, by tweaking those numbers, pick a few more of the right call sites to inline, which would, we will probably pick a few wrong ones as well, but that's fine. I mean, on the average, we have to pick a few, the right ones. And if we, for example, the loop penalty is somewhat fiddled, and then your bench, like the case study you had where one of the calls was in the loop, now finally gets inline, cool. Now you get all the benefits by just fiddling with this one number in theory. And it's unclear to me that why we don't compare it, where we couldn't do auto-tuning on more than one benchmark, because you said, oh, you would tune it on one application. We could tune these numbers on more applications. That's not the thing.
I think that there's a bit of a, I don't know, what the expression is, red herring. Okay, there's a bit of a, okay, I don't know if, so more inlining doesn't actually mean, so more inlining to me means something more like hand wavy and informal. It's not actually something that formally carries any meaning, right? So what I'm getting with that is that even in the example that Amir gave there with the benchmark where he did some deep analysis, it seemed quite obvious. So it's not so much about the more inlining, it's like better inlining decisions were made, right? So the default heuristic was picking this one, right? So the default heuristic was picking something. The auto-tuned heuristic discovered additional or like separate opportunities, right? One missing, one fine, but nothing is perfect. So I think that it's not about more; it's about
this example. This example is showing exactly what I'm trying to say. It's more.
Okay.
So by default, O3 inlines 1 out of 3 call sites. The auto-tuner, like perfect result, is inline 2 out of 3 call sites. The aggressive result is inline 3 out of 3 call sites. So in their model, Amir's model, inlines all 3, which is better than inlining only 1, which is what O3 does, but not as good as inline. So in this,
I see your point here, but let me jump in here because so we have a large set of auto tuning results when we were trying to base our MLGOPerf with, and in many cases, aggressive inlining would lead to a slowdown. In that specific case that I could find in a short amount of time I had to prepare for the presentation, in that specific case, yeah, we inlined all of those 3 major call sites, and one of which was wrong, but the other 2 led to have a higher speed up. But in many cases, O3 was actually among top 20% good results. And like in larger applications, when we aggressive inline, we just slow down right out of the bat. Yeah.
I mean, I'm not saying all of this is wrong, and I'm not saying, this is not what we should do. I'm just saying, from the data presented, one can arguably say, hey, maybe we just, our heuristic is wrong. That is, I think, the conceptual part why we want these models, because we don't know if our heuristic can even pick up the few call sites that we don't inline, or avoid the call sites that we currently do inline, where the decision should be swapped. And we have at least hope that of the models we can learn this eventually in a proper way. And that's kind of the conceptual reason why to do this. Yeah, but then that has to be, for all the people that doubt this, that has to be kind of made explicit, because the numbers alone are snapshots, not necessarily conceptual changes. Anyway, sorry, I took enough time. So there were other questions earlier.
Well, I think the vendor left, or is he back on? Can I ask if nobody has a question, I had a few, but I don't want to. Okay. So thanks, Amir. Are you gonna ship this in the stream?
So I guess for that answer, I guess my team leads are also in this call, Tom and Brian. If feel free to jump in for any other details you wanted to provide on this work.
So we're going to look into whether we can upstream it. Obviously, as you know, we have to make sure that the company's okay with that. Like, I think it would be okay, but we gotta go through the paperwork to do this.
I see. Okay, because that'd be awesome. Like, the other question I had was, so this is very low level detail, but okay. So okay, so you go. I'm only thinking about the new pass manager, because for our organization, the other one doesn't basically exist anymore. Like, so you carry out inlining for SEC, and then we run the function simplification pipeline. Where in this picture do you collect? So first about MLGOPerf, where in this picture is MLGOPerf fitting? You see what I mean? Are you collecting MLGOPerf after all inlining, which includes function simplifications?
So are you referring to the training of RL using MLGOPerf, or you're referring to the first phase for which train MLGOPerf?
So first, let's do phase 1. So in phase 1, where do the features for MLGOPerf come from?
Right after the inline pass. So we registered the.
So by inline pass we mean all the module was inlined, right? So that's what you mean by inline pass.
Yes.
Or Okay. So yeah, because the confusion to me was like Elon pass could mean the actual execution of the SCC pass, which executes many times, right?
Mm-hmm.
But you mean the entire module was inline, function simplified, we're done with inlining, we'll never touch it again.
Mm-hmm.
And now it makes sense. Okay,
Yeah.
because then you have a final shape. Yeah,
Right.
and then that probably gets me to: is it correct that you collect the reward at the end too? So you collect the reward at the same place. So all inlining is done at finish, and
Yes.
done in the same place that you collected out. Perfect. Yeah, got it. Okay, that makes sense. Thanks. Okay, that makes sense. And I was gonna say, and you calculate speed ups, and that's where you can sum them up. Yeah, this one. Yeah. So you have programs, right? Okay.
Yes, actually, the actual speed up with respect to O3 is actually coming up from perf, and then perf gives you the amount of percentage of time spent on that specific one, and then you can just have a small math to just correlate certain percentage to the overall CPU cycle, and then find the specific time that each of those call site or function has been spent into.
So so let's say I have a function that calls another one, right? And you're not carrying out the inline, right? So you're saying you're looking at the CPU time, like so CPU samples that you collect per caller.
Mm-hmm.
I see, and then when you look at the fact that you have to collect two, if you don't carry out the inlining, help me out with my reasoning a bit. Like I'm trying to understand how is this.
Yes,
So
obviously one downside of this approach was to on several, nested function are normally an outsider to begin with, but like if you have multiple calls nested to each other, this would doesn't generate the guaranteed results, but in 99% of the cases you don't have this phenomena, right? So when you perf the binary, it's going to give you a list of the percentage spent on that specific function call set, and then you can, using the overall CPU time, you can allocate the specific time spent on that function, and thus dividing that to this is going to give you the actual execution time spent on that. Dividing that to the baseline is going to give you the actual speed up respect. Yeah.
I see. No, okay, I understand this better now. Okay, so you're doing it. You're literally taking every function as its final shape. You're not looking at what does it call anything. You're looking at the CPU samples collected right with perf. I see. Okay,
Yeah.
okay.
Because it's always a tricky case to, as I mentioned in the challenges, when you go finer grained than even module, execution time of a module is also a tricky estimation. But even lower than that would be harder. Because code size, you can always accumulate the code size. It's pretty easy, but on execution time, divisions doesn't work that well, right? In compilation flow.
So, but you do have profiles though, right? Like
yes.
As features.
Yeah.
Right. Okay. And you factor them in when you do the IR part of the R2Perf. You have the basic low frequency somehow captured in the edge.
We added that into the feature of RL on the RL side. Yeah. I mean,
not in R2Perf?
No, not that R2Perf, because these two features are characterizing different scopes for us. One other thing that I wanted to mention, and I mentioned in the paper, the specific hash commit that we forked off from the MLGO. And lately, when I checked back, your GitHub page had added many more features to the RL side. So several of those might be also making the results much better. But at the time when we forked off, we were having only 11 RL features. So we added this block frequency and maybe loop level on top of that. So we are having maybe 13 features on the RL side.
Right. For size, we didn't add any. Like for size, indeed, we added a ton. Like we basically decomposed the analytical models evaluation, but there's no, intentionally no performance. Like size is only size.
Yes. Yeah.
Any performance results are accidental, positive or negative.
Yeah. True.
Okay, but you do include some sort of features capturing profiles in the. Okay, that's interesting.
Yeah.
I'm very curious. Like, did you guys? And I understand that I'm pressing on this, but just because I'm code centric, like, are you guys? I understand that you're talking about. I heard the thing about like shipping in upstream, but is this available in your fork, or your fork is also private?
Our fork is also private. Yeah, it's internal.
I see. Okay. So then, either way, it's about that sign off that you guys need to do internally. It'd be great if this made it upstream, because I mean it's just awesome to be able to build up on it, right? So, and like you said, like a bunch of these things, like having an IR model that can give you a latency estimate is something that we didn't have. We only had that. I mean, the only thing that I'm aware of is like at the level of machine IR, like iCumble and those guys, but it's way too late, right? So
There has been a basic block-based model years ago from MIT, I think.
Yeah, iCumble, but
Yes.
not IR level, right?
Really? Oh.
Yeah, it was. It's machine IR, actually, not even machine IR. It's
It was
other-
basic block. Yeah.
Yeah, but basic block machine level, like.
So I have a question about the function model and the basic block
Sure.
model. So for a basic block model, I can understand it because there is no branch there. So every instruction will be executed exactly once. But in your function model, you are timing the time the function gets executed, but there may be variance in terms of like how many times the loop is repeated or which branch the code go
Yes.
for the exact time you are timing this function.
Yeah.
Then how are you going to basically predict the runtime under that scenario?
Yes, this is also a very good question. Yeah, as I mentioned in challenges, this is also one of the things that at best we can do a noisy estimation. But here on the IR2Perf, we rely on perf. So perf shows how many times that a specific function has been called, right? So you have the accumulated time. You can divide it by the number of times. Also, we provided a few features on the IR2Perf side so that it's going to guide the model towards its target, which is the speed up with respect to its baseline, so that these two together provides us as a proxy to the problem you mentioned. Yeah, but that's definitely it's always the case that we might have a noisy maybe CQ cycle per functions. Yeah, because it is a really difficult problem to find that.
So then the question is that why do you choose to use your own train your own IR2Perf model instead of using the basic block level based performance models?
Because IR2Perf it works at function level, right? So and it's tailored towards post-inlining speed up prediction only for inline optimization. So if you use that for other maybe optimization, it might not work as perfectly. So this is somewhat a customized prediction model only for, at function level, what's going to happen when you do an inlining decision, what's going to be the outcome of that regarding to its baseline, right? This is a very, I mean, they were like more generalized prediction models, but I'm sure that they wouldn't have been working with the amount of error we had. I mean, we are not also working optimally, but like the amount of error we had is much less than the rest.
Mm-hmm. Okay.
Yeah.
Hey, can you go a slide actually a bit in front? There was something that you talked about loop unrolling.
Unrolling or
Yeah, loop unrolling something and some more.
Oh, at the end maybe. Oh, by the way, I'll share the slides for sure. Yeah.
Right, thanks. Yeah, and the video or paper, whatever you can.
Sure.
All I say is like you can totally do it in like.
Maybe here.
So, I'll be honest, you kind of lost me there. So if it's not a short, Okay, maybe I can follow up offline because I didn't actually understand what happened here.
Here on this result.
Which is very unhelpful of me.
No. So
sorry about that.
this is live.
So did you try to also train unrolling?
No. So we now you see when we have the release model of MLGOPerf, we have 3 versions now. We have the vanilla 03 compiler. We have the one embedded with MLGO, the one embedded with us, right? So now we have 3 versions. So we thought, okay, let's take into account the inlining that each of these versions bring to the table, and then only tune 2 subsequent passes after the inlining. So loop unroll and loop vectorize. And we'll see what would be the effect of the inlining of these 3 versions on the subsequent passes that we tuned. We wanted to see how much more opportunity each of these models can provide. Yeah.
Well, when you say tuning, you mean like you built an MLGO loop unrolling model?
No, it just an auto tuner methodology. Like you explore the combination of permutations.
Got it. Thank you. Okay, got it. No, I got it. I thought that there was like a miss in this. I was like, you guys also doing it twice more.
Oh, sorry.
Like, there's only one slide, and I was like, okay, got it.
Yeah.
Okay, I see. So it's kind of like a headroom evaluation of like, hey, if you do this, then there proof of existence that you can actually get more, but it's not. There's no statement about like generalizability or any of that because it's not a goal. It's just a headroom estimate.
Right. Exactly.
Right. Cool. Okay.
Yeah.
Okay. Got it. Thanks.
No problem.
Yeah. Oh, and the other thing that I was going to mention is you can look at the thin LTO instead of full LTO. It's more like I noticed earlier a couple of slides were talking about LTO and inlining, and if you do thin LTO, you basically have the exact same pipeline that you have right now.
Right.
It is a link time optimization, and basically the rest of the slides are the same, basically.
I see. Yeah, it would just we thought about this, but we thought it would be another set of a pipeline on top of the one we have, and then it would just make the ML debugging, I would say, more difficult. Otherwise, it's the same methodology. Yeah, at least we know where to debug now. If it was going wrong on the second side, debugging 2 different, let's say, branches of a tree, it would be very hard. But I'm pretty sure there is a lot out there to be gained.
We did a bit of playing with this with the size one within LTO, and it turns out that you could choose to not carry out any inlining in the front and just do it all in the back, for example, or do default in the front. But yeah, the problem is there. I'm just saying, like, we did a bit of playing with that with some positive results. So if link time optimization is important to you, and you don't need to do full LTO and thin LTO is sufficient,
right?
You can actually, you can get some results probably without, you don't have to change your code. Basically, it's just a matter of where you collect the data.
Right.
So, in fact, that's a nice thing with LTO. You basically, it's exactly the same compiler. It's just you collect everything in the back rather than in the front. So,
that's true.
Anyway, okay. This was super interesting. This is really cool, and it'd be awesome if it made it upstream. That'd be great. Any way we can help, very happy to.
Sure.
Okay, there's no other questions. Let's thank Amir for the awesome presentation.
Thanks for having me. Thank you very much.
Absolutely, yeah. And let me know if you have trouble linking these things there, on the page. Thanks for recording it too.
Sure.
Okay.
Yeah.
Let's stop here then. Bye.
Okay. Thank you so much, everyone. Have a good day.
All right.